Good morning, everybody, and welcome again to the CEIA Maths tutorials. Today we've got Frank O'Keefe, who you've met before. He's going to do statistics for you today. So over to you, Frank.
All right, thanks, Eamon. Hi, my name is Frank O'Keefe. I work for CommScope. That's a telecommunications company based up near the airport. So I'll be covering statistics today. So just a quick look at the agenda. Right, so we'll be covering some introductory topics on frequency distributions, measures of center, measures of spread, and correlations. I'll try to get through that fairly quickly before we get onto the meat of the topic, which is to do with normal distributions and the various statistical problems associated with them. There's quite a lot to go through, so I think I'll just get started and get started straight away. Okay, so let's start on frequency distributions. So generally speaking, with statistics, you'll have a data set of some sort, a collection of observations. They may be numeric or non-numeric. We'll only deal with the numeric ones here. And here's an example set. It's just a random set collection of numbers. You might, for convenience, order them, and you'll see that some numbers never come up at all. Some come up once and some come up multiple times. So typically then you draw up a frequency table of each number and how often it shows up. So for example, number 5 shows up twice, number 8 shows up 4 times. So this is a frequency table representation with each data value and its associated frequency. Now you could plot that on a bar chart or call it a histogram with each data value and the associated frequency as the height of the bar. And you'll see some kind of a pattern for the distribution. Now, there are various ways of doing it. You don't necessarily need to have intervals of 1. So you could group, say, intervals of 3 together. You get different frequencies then for the groupings and a coarser granularity on the scale, but it's the same general idea. Now, in statistics, we normally work with large data sets. So with a larger data set, you'll see many more of these bars in a bar chart. Could run into thousands or even millions. And as the number gets greater, you see these bars getting thinner and closer together. So when that happens, you tend not to use a histogram anymore. And what you do is just use the top points of the histogram and join them together in a curve. And that is what you see over here. You move the bars, then you get this curve, and that's called a frequency distribution curve. It's the same idea as the histogram. So for example, you might pick off number 60 here and say that, well, that's roughly 7 or 8. So the number 60 occurs, say, 8 times. Just to remind you that there are other representations like pie charts and so on, which you should know about from the junior cert and you should still remain aware of. And there are measurements like quartiles and percentiles that you should also be aware of. I'm not going to dwell on those now because they're not really the meat of the course. And we don't want to spend too much time on that, but you do need to be aware of these things. Right. We talked about a frequency distribution. Now, very often you'll choose to normalize a frequency distribution. And normalizing means taking a general frequency distribution like this and scaling it vertically so that the area under the curve is 1. And the way to do that is to work out the area under the curve of your original distribution and just divide every y-axis or every y dimension by that area. And then you end up with a curve that's scaled vertically, in this case downwards, in such a way that the area under that curve is 1. And formally, this is the way you do it. You work out the area of your non-normalized curve and derive every point, or divide every point in that curve by this area A to produce your normalized frequency distribution, which then satisfies this criterion that the integral over all x of this normalized distribution is 1. The reason you would do this is because you've now said that the sum of all of these values is 1, and that corresponds to probability, because the sum of all probabilities should always add up to 1. And when you've normalized the frequency distribution function, you end up with a probability distribution function. So you've now got a curve that represents the probability of any particular data value, any particular x value. Okay, just to emphasize that again, a normalized frequency distribution is the same as a probability distribution function. And the way you would interpret it, if you have a normalized frequency distribution here along an x-axis, then the area under the curve between any two x points, A and B, is the probability that a value x lies between A and B. And that's important. We'll be seeing that with the normal distribution later, how to use this to calculate actual probabilities. So a special case of the probability distribution function, which is the normalized distribution function, a special case of that is called the normal distribution. It has other names. It's a Gaussian curve or a bell-shaped curve, as you can see from its shape there. It's bell-shaped, and it represents a lot of random processes that will be encountered in reality. And I've given a list of some things there that you might expect to show a normal distribution pattern. For example, the weights of a collection of objects, like if you had 1,000 potatoes and you weighed them all, you'd find that there was some average weight, but some potatoes were smaller, some bigger. As you get further away from the average, it becomes less and less likely, and so you see this drop off of a tail as you get further away from the average. So this is the normal distribution, the bell-shaped curve, and pretty much every problem you'll encounter in the leaving cert statistics is to do with this normal distribution. Now there is another variant on the normal distribution that's called the standard normal distribution. And that's just a scaled and shifted version of a normal distribution. It's a particular case of a normal distribution. It's got a standard width and it's centered around the x equals 0, or they actually change variables when they go to this standard normal. It becomes a z variable. So it's centered around and symmetrical around the z equals 0 axis. It's still a bell-shaped curve. It has a standardized width, whereas a normal distribution is bell-shaped but has variable width. Okay, so let's diverge for a minute and let's talk about measures of center, which are loosely called averages. There are various kinds of average. You need to be aware of them. The mode, the most common value, which may or may not exist in a data set. The median, which is another name for the 50th percentile, that splits a data set in half. and the mean, which is the most important one, and it's the one we'll be dealing with most. And that's what people generally mean when they talk about an average. The mean, which can be referred to by the letter mu or by the letter x bar. And it's just the sum of all values divided by the number of data points. And that's equivalent to saying the sum of the frequency times the value divided by the sum of the frequencies. It's a slightly quicker way of calculating the same mean. If we look at our particular data set there, we can see how to calculate the mean. You could just add up all these numbers and divide by the number of numbers, the count, which is, I think, 20. But it's slightly quicker in this case, but generally it's much quicker to multiply each data value by the number of times it occurs. That's to say, each data value by its frequency, and add those up, and then divide that by the sum of the frequencies. And in this case, it generates the value 8. So as I say, we'll be concentrating on the mean for the whole Leaving Cert course, actually. Now, measures of spread, also important. And again, there are various measures of spread. There's a full range from 4 to 12 is one measure of the spread of these data values of this data set. There's an interquartile range. So that's basically you take the 25% point and the 75% point in the ordered set and the gap between them. But most importantly, and the one we'll be talking about exclusively, is the standard deviation. If you want to remember how to calculate it, remember that it's the root mean square deviation from the mean. That is to say, you have a mean value and you want to measure or characterize how far away on average all of the data points are from that mean value. Now you could just take the average of the deviations from the mean, but that turns out to be 0, almost by definition. So to get something useful, they tend to square the deviations from the mean. So each data value x is some different distance from the mean mu, and that's x minus mu or xi minus mu for the ith data value. If you square that and take the average of those square values, the mean of those square values, I should say, then you'll end up with a measure of spread. Typically, though, you'll take the square root of that again to bring it back to the same dimensions that you started with. So it may be non-intuitive, but it is universally used in statistics as a measure of spread. And you can calculate it this way, just using each data point, or you can calculate it this way using the frequencies of each data value. And in our data set, that's how you would work it out. Now, you're unlikely to have to work it out by hand, but I just illustrated how you would in this case. Right. So the standard deviation, what does it mean? Well, it represents how spread out the numbers are. So here's an example of one frequency distribution with a small standard deviation. We'll call it sigmas, generally the letter used. So this one has a standard deviation sigma 1, which is quite small. Here's a much more spread out data set with a larger standard deviation. And that's sigma 2, I've called it here. Note that these two distributions have the same mean value. And for a normal distribution, the mean value occurs at the peak of the curve. Okay, now let's talk about bivariate data for a little while. It's a bit of a diversion from the main portion of the course, but you do need to know it. And in this case, we're looking at the relationship between two variables. And examples of that might be, if you look at how one factor is dependent on another. And you'll see often surveys and reports done. I've given an example here of life expectancy versus years of education is something that's often studied. If you're into astronomy, the size of a star is related to its color, which relates again to its temperature. There's a famous diagram in astronomy called the Hertzsprung-Russell diagram. And the majority of stars lie along a particular curve in that diagram. And the reason you would study the relationship is that you might find correlations, and sometimes those correlations indicate there are causal relationships. Like, for example, does having more education lead to a longer life expectancy? Now, you represent these relationships graphically on what are called scatter plots, where you plot the x value on or one variable along the x-axis and the other variable along the y-axis. And you get a set of pairs of the two variables. So x1, y1 is one data point, x2, y2, and so on up to xn, yn. Often you want to see if there's a correlation between the two variables, which would indicate the possibility, at least, that the y variable would be dependent in some way on the x variable. And we show a case here of a positive correlation where there's a tendency as x increases for y to increase. That's called a positive correlation. It doesn't mean that x increases every time that y increases every time that x increases. You can see a particular case here. If you go from there to there, y actually decreases for an increase in x. But for the most part, there is an increase in y when there's an increase in x. And you could imagine, many such relationships. Population of a country, for example, tends to be related to its area. So larger area would generally produce larger populations. You'll find exceptions to that. Here's an example of a curve that would indicate a negative correlation. As x increases, y tends to decrease. I've given an example there. Famously, the number of cigarettes smoked per day results in a reduced life expectancy as the number of cigarettes increases. Sometimes, though, there is no correlation, and you can't pick out any particular trend, and that's called uncorrelated data. I've given an example there of something which is obviously there would be no reason to expect a correlation between the size of an animal and the size of its name. Now you can quantify the level of correlation. I've given the formula there. I don't think you need to know this. I believe it's in the log tables anyway, and you certainly wouldn't be asked to work that out. This is just to illustrate that it can be calculated. What happens is you end up with a correlation coefficient, and you should know what that means and what it represents, and how to interpret it is that if R is close to +1, you've got a strong positive correlation. If it's positive but not close to 1, then it's a weaker positive correlation. If it's close to -1, you've got a strong negative correlation. And if it's negative but not close to -1, it's a weak negative correlation. And if it's close to 0, then it's most likely uncorrelated. So to illustrate that, This is a strong positive correlation. You can see a very clear relationship, a very clear trend. This is a somewhat weaker positive correlation. There is a general upward slope, but it's not as definitive as for the strong case. Here's a strong negative correlation, very clear relationship there. And here's a weaker negative correlation in this case. Now, to look at the relationship, you might try to, if you do see some kind of a correlation, you might try to do data fitting or curve fitting. And very often you'll try to fit a line. In this case, you've got a weakly correlated positive correlation between X and Y. And you might try to represent that by a linear representation by fitting a line to it. That's called linear regression. Calculators can do this for you, and they'll work out the slope of the line, the slope and intercept of such a line. But you can do it roughly by eye, just by following the general slope and trying to keep roughly half the points above and below the line. And you might try to run it through the average point, the average of the X's and the average of the Y's, but that's not strictly necessary. Once you've drawn the line, then you would measure its slope the usual way and its intercept on the Y-axis. And then you can work out the relationship. You can express the relationship as Y equals mx plus c. Okay, so let's get back to the normal distribution. As I say, this is the most important part of the course, and virtually every exam question I've seen is based on a normal distribution. Right, there are two parameters that define a normal distribution. There's the mean value mu and its standard deviation sigma. Now, sigma is a measure of spread, as we said. So sigma is, in fact, it's represented here, 2 sigma, going from the mean plus sigma to the mean plus minus sigma. And that covers the bulk of the peak of the curve. And in fact, 68% of all the X values lie between the mean minus 1 standard deviation and the mean plus 1 standard deviation. So that's mu minus sigma to mu plus sigma is 68% of the area on the curve is there. So there's a 68% probability that any X value will lie within 1 standard deviation of the mean. Now, more interesting is if you go 2 standard deviations out, you find that almost all of the curve lies between those 2 points. Within 2 standard deviations of the mean, you get approximately 95% of values. And within 3 standard deviations, it's even stronger. It's 99.7% lie between there and there. Now, it's important to remember this empirical rule, or at least the middle one of those, which is the 95% rule. 95% lie within 2 standard deviations of the mean. Between here and here, 95%. And that will be used over and over again in statistics and in exam problems. This empirical rule. If you want to be strictly accurate, and you probably should be, it's not quite 2 standard deviations. It's 1.96 standard deviations. So you should remember that. But this empirical rule is used at least 50% of the time in exam problems. Okay, let's talk again about the standard normal. First of all, the general normal distribution here has a mean mu and a standard deviation sigma, and mu and sigma can vary, so you can get narrower or wider distributions, and they can be positioned around different averages. A particular case then is the standard normal, when you set that mu to 0 and you set the standard deviation to 1. This is a standard normal. And when you express it as a standard normal, instead of an x variable, you talk about a z variable, which is sometimes called a z-score, or a, in the case of sample data, it's called a test statistic. The reason you would use this standard normal is because there's only one of them. There are infinite numbers of different normal distributions with different means and different standard deviations. So you can't plot all of them, or you can't tabulate all of them, but you can tabulate this one standard normal. And you'll find this in your log tables. So quickly switch to the log table. And there's an older version of the log table. I imagine it hasn't changed much though. And you'll find the tabulation of the area under the standard normal curve. These are the tabulated values here, and these are the values of z down on the left. And it goes all the way up to z equals 3 in this case. Okay, so, and it's very important to know the relationship between the normal distribution and the standard normal. A good number of exam questions rely on that. So looking a bit deeper at the standard normal, how do you get there? How do you convert a data set or data value from a general normal distribution, which is the real data you will measure, to the standard normal? And what you do is you change variables. You change from a variable x, which is your sample data, to a standardized variable z, which is called the z-score. And you do it by subtracting the mean, mu, and dividing the result by the standard deviation. And when you do that, if you think about it, what you've got is something that measures how far you are from the mean. And because you divide it by sigma, what it represents is it's the number of standard deviations that the value x is away from the mean value mu. Okay. So you should try to understand that interpretation of what z is and how it relates to x, your test variable. Okay, so how do you use the standard normal? You need to use the tables, and the tabulated values for the standard normal. What's tabulated is the area under the curve up to a certain value z1. And then the value in the table represents the probability that any value z is less than or equal to your specified value z1. And in many cases, that's exactly what you need to calculate, but sometimes you can't quite read it directly from the table. One problem is, if you look at the table here, is that it starts at a z of 0 and goes up to z of 3. That is that's useful, but sometimes you need to work with negative z values. So you really only got half the table here. And you need to work around that. And another thing is, as well as getting a negative z1, you might have a problem where you want to find the probability that z lies between two values, and that you can't read that directly from the table. So you need to use some tricks for working with the table. And I've listed these tricks here. You must use the fact that the graph is symmetrical. about the y-axis. Use the fact that the total area under the curve is 1, because it's a normalized distribution. And then you try to work out the area you're looking for in terms of sums or differences, combinations of areas that are tabulated. So I'll work through some examples of that to illustrate that. So, for example, what if you need to find the probability that a particular test score is greater than -2? Now, you'll often see it written as greater than or equal to. It actually doesn't matter in statistics whether it's greater than or greater than equal to, because the probability of it being equal is 0. So, but it's conventional to write it as z greater than or equal to -2. So if you want to find this probability, we can represent that probability by this shaded area under the standard normal curve, starting at z equals -2. But that area isn't tabulated. What is tabulated is something that is the mirror image of it, is this probability that z is less than or equal to, and I've got a typo here, sorry. I got 2 typos there. This should be z greater than or equal to -2, and this is z less than or equal to +2 there. Sorry about that, there are 2 typos there. So this shaded area is the probability that z is greater than or equal to -2. So scratch that. But you can see by symmetry that it's equal to this shaded area. Just flip this whole thing around and you get the same area, but now it represents the probability that z is less than or equal to +2. So looking at our tables, we've got it in this form now. We've got a z1 equal to 2. So looking up here, z1 equals 2, and it's 0.9772. Now, if it was 2.01, we'd be looking here, 2.02 would be here, and so on up to 2.09 out here. And then 2.1 goes on to the next row. In this case, it's just 2, so it's 0.9772. So what that's saying is that this area for the probability z less than or equal to 2 is 0.9772. And then by symmetry, the probability that z is greater than or equal to -2 is 0.9772 again. And how do you interpret that? Well, you say that 97.72% of all data samples are greater than a value 2 standard deviations below the mean. This is your value that's 2 standard deviations below the mean. 97% of values are greater than that, 97.72%. Okay, that's a simple example. Let's have a look at a slightly different answer, or different problem. What's the probability that z is greater than 2? In this case, that's represented by this shaded area here. But that's not tabulated. What is tabulated is this area here. We're calling A1. So A2 is what we're looking for. A1 is what's tabulated, which is the probability that z is less than or equal to 2. And so we look up this. This is the same number we just looked up. It's 0.9772. We use the fact that A1 plus A2 equals 1. So A2, which is the number we have, is 1 minus A1, which is the number that's tabulated. Or you can say, write it as the probability that z is greater than or equal to 2 is 1 minus the probability that Z is less than or equal to 2. But this value is 0.9772. We just saw, same value we had before. So subtract that from 1 and we get 0.0228. And that means that 2.28% of values lie more than 2 standard deviations above the mean. I'll do a couple more examples here because this is important. You should get practice doing this. It's very important for solving exam questions. Right, so we want a probability that Z lies between 1.54 and 2.56. Obviously, that's not a tabulated area. It's this area that we're looking for here, but it's not tabulated. And I've called it the area A2 there. How would you work it out? Well, what is tabulated is area A1 up as far as 1.54, this area. What's also tabulated is area A3, which is this area up as far as 2.56. And obviously, this area A2 is the difference between those two areas. And so A2 is A3 minus A1. A1, we know, is tabulated for p z less than or equal to 1.54. So let's look that up. 1.54, here's 1.5. Go over to here, we get 0.9382. 0.9382. A3 is the probability that Z is less than or equal to 2.56. So let's go over to our tables, and it's 2.56, 2.5. Go up to here and get 0.9948. 0.9948. We subtract those two and we get 0.0566. So 5.66% of Z values lie between 1.54 and 2.56. Okay, and I did one more example. Again, this is a slightly trickier one. You want probability that Z lies between -2 and 1. And this is tricky because we're using a negative Z here as well as getting this area. So how do you do it? Well, this area A, try to express it in terms of areas that we can work out. And it's area A1 minus area A2, where area A1 is the curve up as far as here, and area A2 is the curve up as far as here. But unfortunately, area A2 isn't tabulated because it's a negative value of Z. So you've got, again, to use the symmetry of the function and say, well, here's an area which is the same as area A2, but it is tabulated. Well, it isn't actually, it's the area A3 is tabulated, which allows us to work out area A2. So let's work through that. Area A1. Area A1 is probably the Z is less than or equal to 1. So let's look for that in the tables. And here it is 0.8413. Area A2 is the probability that Z is less than or equal to -2, which is the same as 1 minus the probability that Z is less than or equal to 2. So it's 1 minus this area here. And we already had that, which was 9.9772. So it's 0.0228. And subtract the 0.0228 from 0.8413, and we get 0.8185 for this area here, which is the probability that Z lies between -2 and +1. Okay, so it's a little bit tricky working through it. You need to keep your head on and use the tricks, use the symmetry when you're stuck with a negative Z value, flip it around, and use the fact that the areas all add up to 1 when you're getting a an area like this for Z greater than a number. Okay, so this is something you do need to practice. Get used to working out these probabilities from the normal tables. Okay, now a major part of statistics, and I'd say probably about 50% of the exam questions you'll see are on inferential statistics. What does inferential mean? Inferential means you need to infer information, which means you need to draw a conclusion from limited information or limited data. And that generally means that there's some sampling going on. So in statistics, instead of measuring every data point, you often look at a sample and measure the characteristics of the sample. And you try to infer information about the whole population of data points from that limited sample. So, as I say here, it's an imperfect, the sample data is an imperfect representation. And so you have some questions. What can you infer about the population, the whole population from the sample? How confident can you be in what you've inferred, and what margins of errors are there on what you've inferred? Now, there are two classes of these inferential problems. There are sample proportions, and you would like to infer population proportions from those sample proportions. And there are sample means, and you'd like to infer population means from the sample means. So what do I mean by proportions? If you know, if you're trying to find out what proportion of the population have some characteristic. Here as an example, let's say what proportion of the population has blue eyes. So you might take a sample of 100 people from the population and try to deduce what population of the general what proportion of the general population has blue eyes from that. Your first guess would be 40%, but you need to know how reliable that 40% is. Similarly, you could be working with means. You might take a sample of, say, loaves of bread, weigh them, find that the average weight is 800 grams. What does that tell you about the average weight of all loaves of bread from the batch or from the whole production run? Again, your first guess would be 800 grams, but you need to know how reliable that is and how accurate that is. So those are the two classes of problems that you'll be looking at. But to do it, you need some rules of thumb and some results from general statistics. So let's start with the inferences about proportions. One thing you can say that is if you measure, if you were to measure an entire population and found that some proportion had P had a characteristic, then you would also expect that if you measured a sample of that population, that a similar proportion would have the same characteristic. But this, because you're working with a small sample, you might not get an exactly the same proportion from the sample as you had from the whole population. So you have some error in this measurement, P hat, which is the measurement of the proportion in the sample. So the notation here is that P is the proportion in the whole population with the characteristic, and p hat is the proportion measured in the sample. So what kind of error would you expect to get in this sample p hat? And the error is called the margin of error, referred to as E. It's the size of the difference between your sample measurement and the true measurement. And you can express it this way, that the sample measurement will lie plus or minus a margin of error from the true measurement. So it'll lie between P minus E and P plus E. So it'll be between the true measurement minus the margin of error and the true measurement plus the margin of error. When I say true measurement, I mean the measurement of the full population. Now, the size of this margin of error will depend on how confident you want to be that it really lies in this interval, within this margin of error. It also depends on the sample size. Now, I've expressed it this way, but generally speaking, you can flip this around and say, well, if we measure this p hat from a sample, what's the likely range of values for the true population proportion p? And then you flip it around and it's saying that, well, the true population p lies within a margin of error E of the measured sample proportion p hat. And this is the more common way of using it. Right? Both of these formulas are somewhat equivalent, but this is the more common way of framing the problem. You measure p hat from a sample and you try to work out what the range of values of p can be. But to do that, you need to know what the margin of error is. And there's a quick and dirty calculation. For a 95% confidence interval, which we'll talk about in a minute, the margin of error is given by 1 over root n, where n is the number of samples, number of items in the sample. And because this is the margin of error, the range of values of p lies between your measured proportion minus this margin of error and the measured proportion plus the sample of error. And this is called an interval. The distance between this lower value and this upper value is the interval, is the range over which you would expect p to lie. But this formula works. It's 95% likely to be true. So this is called a 95% confidence interval. We're 95% confident that the result lies inside this interval between this lower value and this upper value. As I say, this is a quick and dirty calculation, but it's reasonably accurate, particularly when the values of p and p hat, which are similar to each other, if they're close to 0.5, then this rule of thumb is pretty accurate in that case. But there's a more accurate, a more exact formula, and that is to say that the standard deviation of the sample proportion is given by this formula. This formula is in your log tables. It's slightly different representation. They use the letter Q to represent 1 minus P in the log table, but it's essentially this formula in your log table. Since this gives you the standard deviation, remember the the rule that 95%, this is the empirical rule, that 95% of samples lie within 2 standard deviations of the mean, or to be accurate, within 1.96 standard deviations of the mean. That means your margin of error for 95% confidence is 1.96 times the standard deviation of the proportion. So you can write your interval in this way. Your true population proportion lies between p hat minus 1.96 times the standard deviation and p hat plus 1.96 times the standard deviation. So this is an alternative to having the 1 over square root n here and here. It's a more accurate representation, but it gives you close to the same result. If you're wondering why, if you put the value 0.5 into this formula and use 2 instead of 1.96, you end up with the other formula. So as I say, if you want to be accurate, you use this version of the formula with this standard deviation. Now this is for 95%, this 1.96 standard deviations. You could use other confidence intervals like 68%, where you have 1 standard deviation, or 99.7% confidence interval, where you have 3 standard deviations. But it's nearly universal to use 95% confidence interval as being good enough. If you're 95% sure it lies within this range, that's nearly always what you will use. Now, the other class of problems is inferences about means. I think I might take a 10 or 15 minute break there. Right. Just what on the break there, I just fixed that typo I saw earlier. So just to be clear, that should be a -2 up here and a +2 here. Okay, so we were talking about inferential statistics. So let's go back there. Just to recap, the idea of inferential statistics is that you're dealing with a sample from a larger population of data. You want to infer information about the population from the reduced sample. And there are 2 classes. There's population proportions, which you want to infer from sample proportions, and inferring population means from sample means. Okay, and again, just recapping, for proportions, you want to have a margin of error that gives you a confidence interval that the population proportion P lies within a range E, plus or minus E, around the measured sample proportion P hat. And that margin of error E can be approximated by 1 over root n if P is close to 0.5. And then you have a confidence interval of 95% that P lies within this margin of error E around what you've measured for P hat. More accurate method is to work out the standard deviation of this P hat, which is given by this formula. And then use the empirical rule for the 95% confidence interval saying that 95% lie within 1.96 standard deviations of the center of your measured value, which is p hat. Okay, so let's carry on and talk about inferences about means. And what you want to do now is look at a subset of a population, a sample. An example here that you might have a cargo of millions of apples. You want to estimate the average weight of an apple. You're not going to measure every single one. If you did, you would get some value. And let's say that the true value, the true average is 84 grams. But you could take a smaller sample, in this case 100, and you're going to get roughly the same average, but not exactly the same average from that sample. And in the case of one of your samples of 100, you might get 82.7, for example. But if you took a different sample of 100, you might have got something slightly different for the average weight. And a third sample might have a different average weight again. Now, for terminology, for notation, we talk about the population mean being mu, and each of those samples we would call the sample means, we would call x1 bar, x2 bar, x3 bar. And you can take as many samples as you want, but the average value of those sample averages you label as mu subscript x bar. And in this case, where we had 3 samples and 3 averages from those samples, 82.7, 85.6, and 84.8, the average of those averages turns out to be 84.4, which is close, but not exactly equal to the 84. As a general rule, this average will be pretty close to the true average of the population. And as the sample size gets larger and larger, it gets closer and closer. So from that, we can work out how close one of these is likely to be to the true sample mu, true population mean mu. And we do that using the central limit theorem, which you do need to know. And the central limit theorem says that, if you've got a suitable sample, which means that your sample size is large enough, or if the original population had a normal distribution, and in most cases they'll tell you that it has, then these X bars have a normal distribution, which means you can talk about their average and you talk about their standard deviation as usual. But critically, the central limit theorem tells you that the average of these sample means is the same as the population average, and the standard deviation of the sample means is the population standard deviation of the parameter you're measuring divided by the square root of n. Right. So here, mu and sigma are the mean and standard deviation of the whole population, whereas mu x bar and sigma x bar are the mean and standard deviation of the sample means. We need to illustrate that with some examples. Now, again, you'll commonly use 95% confidence interval. So that means you can apply the empirical rule. Or more generally, you can use the z-score. You convert it to z statistic using this same transformation as always, you subtract the mean from your data and divide by your standard deviation. And in this case, remember the mu is the same, the mu x hat or mu x bar is the same as mu, but the standard deviation of x hat is the population standard deviation divided by root n. And then you can use the empirical rule for 95% confidence interval using that standard deviation. And remember, this empirical rule is can be stated this way as well in terms of the Z statistic. Again, sorry, I've got a typo here. There should be minus 1.96 down here. Let me see if I can edit that. Right. Minus 1.96. So Z lies between minus 1.96 and plus 1.96 95% of the time. So this is your 95% confidence interval. Now the last thing we'll talk about, well, two more things actually. First of all, hypothesis testing. Using the confidence intervals we have, we can test whether a hypothesis, that's a belief or assumption, is likely to be true based on the sample data that you have. And generally what you have is a null hypothesis and an alternative hypothesis. The null hypothesis is the default assumption that basically that the population is as expected or as previously asserted. And normally you'd use a 95% confidence interval, which means that the sample mean or the sample proportion should be within 1.96 standard deviations of the expected mean or the expected proportion. Again, that's just the empirical rule. Equivalent to that, you can say that the Z score should be between minus 1.96 and plus 1.96. Again, that's the Z score equivalent of the empirical rule. And if you do meet that condition, then you can accept the null hypothesis. Otherwise, you reject it and accept the alternative hypothesis. And just to be clear, rejecting the null hypothesis means that your default assumption or expectation is probably wrong. Now, the other thing you'll be asked is significance tests, or to work out a p-value. A p-value is the probability that a result or a result as bad or worse than what you have could have occurred by chance. And it corresponds somewhat to the confidence interval. So if you have a 95% confidence interval, that corresponds to a p-value of 0.05. And p equals 0.05 is a case that corresponds to 95% confidence interval, so it means you can use the empirical rule. However, if you're not working with a p of 0.05, then you don't use the empirical rule, and you need to work out the Z score of the results and use the standard normal tables to calculate your probabilities. This all needs to be illustrated with exam questions, which I will do now. Just as a side note, you'll see this referred to a lot in science. Scientific studies have this criterion of a p-value of 0.05 as a test of significance for publication. So it is a widely used value corresponding to 95% confidence interval. Okay, so that's pretty much everything covered. I went through it very fast, and I apologize for that because I wanted to leave time to do examples using exam past exam questions as examples, because I think that's the best way to illustrate all of these concepts. So what I'll do is I go through some exam questions, some of the older ones. There will be some more tutorials where they will go through, I think, recent exam questions. But I'm going to go through some of the older ones in order to illustrate the concepts we've been discussing. For some general hints, take your time when you're reading the question, pick out some keywords. If you see 95% confidence interval or a 5% significance, then they're probably telling you to use the empirical rule. The empirical rule being, in the case of sample means, these are the two accurate versions, that you can go 1.96 standard deviations on either side of a mean for mean inferences, or in the case of proportions, it's 1.96 standard deviations on either side of the measured sample proportion. And here's the approximate version for inferring proportions using the 1/√n formula, which again only applies to the 95% confidence interval. So this is using the empirical rule where you see 95% confidence interval. If you don't see that, then you're probably going to need to work with the z-scores and use the tables instead of using the empirical rule. Okay, so let's look at a problem from 2015. And here, well, this first part, again, part A, they're looking for a 95% confidence interval. You have a sample of 100 shoppers from a larger number of larger population, and they give you the mean spend and the standard deviation. So you want to find a 95% interval for a mean amount spent. Okay, well, you can use the central limit theorem. We're dealing with samples of means here, so the central limit theorem applies. You can imply it because this number 100 is greater than 30. So applying it, you work out the standard deviation of the means as this sigma over √n. Sigma is 20.73, √n is √100, you get 2.073. And then 95% confidence interval is 1.96 standard deviations on either side of this measured value x bar. So you just multiply 1.96 by sigma and subtract that from your measured mean of 90.45 to get your lower limit, and add it to your measured mean 90.45 to get your upper limit. And then this is your confidence interval, your 95% confidence interval. We're 95% sure, based on our measurement of 90.45 and our standard deviation, that we're 95% sure that the whole population of Saturday shoppers spent on average a value in this range. Okay, now following on that same problem, we're looking at a claim, and they say test supermarket claim. When you see tests, you know you're doing hypothesis testing. So the state your null hypothesis, your alternative hypothesis, and your conclusion. Well, your null hypothesis is basically that, it is true. The claim is true. And it's consistent with your previous data. The alternative is just the opposite of that. The average spend is not 94. Now, first of all, again, they're saying 5% level of significance. That corresponds to 95% confidence interval. So we're still using the empirical rule. So we can still use this 95% confidence interval, going from 86.39 to 94.51 that we just worked out. And 94 does lie within that range. And because it does, 94 lies within this range, you can accept the null hypothesis and say that the supermarket's claim is plausible based on the sample. It's plausible that the true average is actually 94 based on the sample that you have measured. Now, part C, they ask you to find the p-value of the test in part B and explain what it means. Well, for the p-value, you need the z-score. The general formula for working out the z-score is subtract the mean from your sample, from your measurement, and divide by the standard deviation. But this is a measured mean, a sample mean you're dealing with. So the formula is the same, but now the standard deviation that you're working with is the standard deviation of the sample mean, which we had worked out before using the sigma over root n formula as this number 2.073. So we subtract our measurement from our mean. Sorry, we subtract our stated value 94 from our measured mean divided by the standard deviation of the means. We get minus 0.171. So Z is minus 1.71. Now the p-value is the probability that this particular score or something worse than it, more extreme or worse than it, could have happened by chance. And what that is the probability that p is less than minus 1.71 is a more extreme, a more far out value. But it's symmetrical that a Z value of more than plus 1.71 is also more extreme than this value. So what we're looking for is the probability of this or this, that's to say the sum of these areas we need to work out. Okay, so the probability that Z is less than minus 1.71 is the probability of a value further from the mean in the negative direction. And the probability of Z being greater than plus 1.71 is a probability of a value of being further than the mean in the positive direction. So let's work out what each of those is. The P that Z is greater than or equal to 1.71, remember, is this area, which is 1 minus this area that is tabulated. Let's look at the table for 1.71. It's here, it's 0.9564. So this area here is 1 minus 0.9654, it's 0.0436, this area. But by symmetry, you can say that this area is the same. So you add the two of them up, you get 0.0872. and that is the p-value they've asked you for. They ask you to explain what this value represents in this context. And this number, it represents the probability that the mean that you've sampled would be as far away as it is or further from the true population mean if that true mean is 94. Now we've got a value of more than 5%. So it's more than 5% likely that this could be true. And so that's not unlikely enough to reject the null hypothesis. So we don't reject the null hypothesis. Okay, so let's move back to 2014, paper 2. And here straight away, again, you should try to classify the question and what kind of problem it is. You see a success rate of 51%. 51% is a proportion. We're dealing with proportions here. So we've got two drugs, A and B. So looking at drug A, they say the drug A is successful from 296 out of a sample of 500 patients. And they're claiming that this is better than the generic drug, which is known to have a success rate of 51%. So you wanted to do a hypothesis test to see whether you can justify this claim. Okay, so let's work through it. Let's see what the proportion for the generic drug is 0.51. The sample proportion for drug A, work it out, it's p hat 296 over 500 is 0.592. They're asking you for a 5% level of significance. That's 95% confidence interval. That's the empirical rule you can use here. And also, since p is very close to 0.5, both of these p's are close to 0.5, you can use the simple formula for margin of error if you like, which is E is 1 over root n. And in that case, it's 0.0447. If you wanted, you could use a full up formula from before, be slightly more accurate. But in this case, this is probably accurate enough. So your confidence interval then is 0.51 plus or minus this margin of error. Right. If the sample proportion P is 51%, we know that it is, then there's a 95% chance that a measured sample P hat would lie between 0.51 minus this margin of error and 0.51 plus this margin of error, which is in this range 0.46 to 0.5547. That's where P hat should lie. We're 95% sure it should lie in this range. It doesn't. It lies outside that range. Now, our null hypothesis here, we'll state it, is that drug A isn't any better than the generic drug. That's kind of the status quo, our default hypothesis. But we haven't satisfied that because our measured P hat lies outside this range, our 95% confidence range. We're going to say that we reject the null hypothesis. It's unlikely that this could have happened by chance, that this measurement of 0.592 could have happened by chance if our true proportion is 51%. So drug A then is likely to be better than the generic. Now they're saying that you've got another drug B, and in this case, you want to find the range where the maximum number of patients, maximum proportion that could be treated with drug B in order to lie within this range, so that you could accept the null hypothesis. Right, to accept null hypothesis, p hat must lie inside this range. And because you're looking at the maximum number of patients, you want to see what's the maximum proportion that could have this, what's the maximum number that could have this proportion 0.5547. Well, the proportion is number x over 500. That must be less than 0.5547. Multiply by 500, you find that x must be less than 277.3. But of course, it's an integer, so the maximum value it can be is 277. Okay, so that was a question on sample proportions. Let's look at 2016 now. Again, we try to classify this problem. There's no mention, at least yet in this part of the question, there's no mention of 95% confidence interval or 5% significance or anything like that. And there's no mention of samples either. So this is not actually an inferential statistics problem, not yet, not part A at least. This is just a plain normal distribution problem. Right, so the question, they tell you a mean and they tell you a standard deviation. And they want you to find what percentage of people will lie outside a particular level. Okay, so we have the mean, we have the standard deviation. We can't use the empirical rule here. So we need to work out a z-score. We want to work out the z-score of 60,000. Well, this is the formula for working out z-score. It's subtract the mean from your sample, divide by the standard deviation. And you work out 1.5944. And that means that 60,000 is 1.59 standard deviations above the average value of 39,400. And we want to find the probability that Z is bigger than this, because the probability that Z is bigger than this number is the proportion of people who are above this value. Right, so looking at that, again, this is a greater than or equal to, we need to use the 1 minus probability to convert that to as from the tabulated value of Z being less than or equal to 1.5944. Let's look at our normal tables. And we find, well, we find the Z of 1.59 is 0.9441. So 1 minus that is what we're looking for, and that's 0.056 or 5.6%. So 5.6% of Z scores are bigger than 1.5944, which means that 5.6% of people will have incomes over this value. Okay, part 2 now. They're looking for a subsidy to the lowest 10%. So you need to look at the Z score of the lowest 10%. And that would be a Z score whose tabulated value was 0.1. So you're looking for a Z value such that 10% of Zs lie below it. That's not tabulated. you could look instead for using symmetry for a Z, I'm calling it Z prime, such that 10% of values are above it, which means that 90% would be below it, right? Because the area under this curve here, all the way from minus infinity up to Z1 is 90%. So you're looking for a value of Z prime such that the probability that Z is less than or equal to Z prime is 0.9. Let's look at the table, 0.9. And now we're not looking for a Z of 0.9, we're looking for a this tabulated value of being 0.9. So we don't go to this here. We search this table for the value of 0.9 and we find it around here. It's closer to this value than to this value. So I would say it's 1.28, right? So Z prime is 1.28 here. 10% of values are bigger than that. By symmetry, 10% of values are less than minus 1.28. So this is the Z value that splits off the lower 10% of the population, minus 1.28. We need to convert that back into an X. This is the formula for converting between Z and X. We rearrange it to get X equals mu plus Z sigma. And it's plugging in the values we have for the sigma and the mu. We get 22,862. Another way of looking at this is saying that because the P of Z less than or equal to minus 1.28 is 10%, this is saying that 10% of values will be more than 1.28 standard deviations below the mean, right? So we're taking 1.28 standard deviations here, and we're taking them away from the mean to find this lower limit that corresponds to this Z value. Again, and it says near zero. Okay. Now, part 3 of this question, and here we're talking about, they say, a sample of workers. So now we are into samples, we're into inferential statistics, and moreover, they're talking about 5% level of significance here. So now, as well as using the central limit theorem, we also need to use the empirical rule here. So this sample gives you this mean, and this mean is different from the other mean that we were working with. The previously measured mean was 39,400. So they say state the null hypothesis. The null hypothesis is that the mean income hasn't changed, is still the old value of 39,400. And the alternative hypothesis is that the mean income has changed based on this new measurement. Okay, we can apply the central limit theorem here because we have a nice big sample. So the standard deviation of the means is sigma over root n. It's the same sigma we had before. Root n is root of 1,000. We get this 408 for standard deviation. So the Z score now for this value we can work out. We can go subtract our value, our mu, from our X, divide by our standard deviation. We get a Z score of minus 2.74. 95% confidence interval corresponds to a Z between -1.96 and 1.96. You're outside that confidence interval, so you reject your null hypothesis and you say the mean income has changed. Now, this is one way of doing this. The other way of doing this would have been to say, okay, this is our sample mean. This is our standard deviation. Our empirical rule for 95% confidence interval is to go plus or minus 1.96 times this around this mean, and we get a range of means and see whether 39,400 lies within that range, and it wouldn't. So that would be another way of saying you can reject the null hypothesis. The two methods are identical. You're just working with Z's instead of X's. But it's just a little bit quicker and simpler to work with Z here and use this for your confidence interval. If you're working with Z's, then the empirical rule becomes minus 1.96 to 1 plus 1.96. If you're working with the X's, the range will be mean minus 1.96 standard deviations to mean plus 1.96 standard deviations. Two ways of doing the same thing. Okay, still on 2016, question 9. It's quite a long question. Here, part B. Again, reading the question, you'll quickly see that they're talking about a survey, which is a sample of 400. So we're talking about inferential statistics, and we're inferences about means again here, not proportions, but means. So we're in the territory of using the central limit theorem, and 95% confidence interval tells you you can use the empirical rule as well. Okay, so you have sample mean of this value and standard deviation of this. So first of all, use the central limit theorem to work out what the standard deviation of the means is. It's sigma over root n, 256, and then plug that into our 95% confidence interval, which is the empirical rule up here. Using this mean, and you find this range, plug in those numbers, you find this range for the mean income of the farmers. And this is the 95% confidence interval for the mean. And then there's just a question, you know, why would you take many samples? And that's so you can get a normally distributed set of means, and the more samples, then the reduces the standard deviation as well. To be clear, making them large samples reduces standard deviation. Okay, finally they ask you, this has nothing to do with the incomes now, this is just a general sampling, and they're talking about into the use. So they're most likely talking about the proportion, probably the proportion that's used for tillage or something like that. This is a question about proportions. You know that because they have a percentage here. But in this case, they're telling you the margin of error, and they ask you to find the value of n. Simplest way of that is to use the shortcut rule for margin of error being 1 over root n. 1 over root n is this 4.5%, which works out as n must be equal to 494. Okay, I think we have time for one more question. As you're probably seeing now, some of these statistic questions can be quite long, but they're not that difficult numerically. But you need to keep your wits about you when you're doing it and identify the type of question in each case. So here's a 2019 question, and there are they're talking about a sample of 800 cars here. So you are talking about a inferential statistics here with a sample, and they're asking you for the proportion of new cars. So it's an inference of proportions what we're working with here. Right, first of all, they ask you, well, first of all, they tell you that 174 were new. They want you to work out the proportion of new cars. In this sample, the sample proportion is 174 over 800, which is 0.2175. And they want the 95% confidence interval. So you can use an empirical rule, but notably here, they ask you to give your answer correct to 4 significant figures. That's quite accurate. And that, combined with the fact that p hat is nowhere near 0.5, tells you that you probably shouldn't use the quick and dirty rule, the 1 over root n approximation. You should probably use the accurate method. So instead of using this approximate formula, use the accurate method. And the accurate method is work out the standard deviation for the proportions using this formula. You get this, and then use the empirical rule of plus or minus 1.96 standard deviations about the measured proportion. And when you do that, you get 1.96 times this standard deviation, which you subtract from the measured proportion and you add to the measured proportion, and you get a lower limit of 0.1889 and an upper limit of 0.2461. So you're 95% confident that the proportion of new cars on this road lies between those two values. Okay, again, we're dealing with that same sample, but now we're dealing with average speeds. So it's inferential statistics again, but now inference is about means. And I give you the mean of the sample and the standard deviation of the sample. And they're asking you for a proportion, but they don't talk about a 95% confidence interval here. So you can't use the empirical rule here. That means you need to work with a z-score. Right, so first of all, let's work out the z-score corresponding to 95 kilometers per hour. And that is, again, the same rule for converting to z. You subtract the mean from your value, divide by the standard deviation, and you get a z-score of 0.6417. What proportion are traveling over 95 kilometers per hour? Well, the table will tell you for a z-score of 0.64, 0.7389, but that's the number that are going slower. That's the probability of being less than this z-score. So 73.89% are slower than 95 kilometers per hour. You need to subtract this 73.89 from 1 to find the proportion that are faster than this 95 that have a Z score greater than 0.64, and that's 26.1%. Now, next part of that problem, a particular driver was told that 70% of all speeds were higher than his speed. And you want to find what speed that must have been. So we're looking for a value of Z, a Z score, which would have 70% greater than it. So we're looking for a value of Z such that this area under the curve from Z up to plus infinity would be 70%. Clearly, it must be a negative value of Z because 70% is more than half. So you have more than half of the curve. So immediately we would tend to look at a corresponding value Z prime that's positive. And that Z prime would have a 70% being less than that value. So it's the same area using the symmetry of this curve. To work out what Z prime is such that the probability of Z less than Z prime is 70%. So we want to find a value of 0.7 in the table. So searching the table, we find 0.7 kind of between here and here, between 0.52 and 0.53. So we take 0.52 here. So that Z prime would be 0.52. If you want to be a bit more accurate, you could say it's 0.525 because it's sort of between two values, but this is probably accurate enough for us. 0.52, that's for Z prime. So Z would be minus 0.52, this Z here by symmetry. Now that we have the Z, we're going to convert it back to an X. So this is the formula for converting between Z and X. Rearrange it so we can get an X from the Z. And we get 87.3, which was the mean, and subtract this number of standard deviations from it, and we get 81 kilometers per hour. So 70% of speeds would be higher than 81 kilometers per hour. Okay, this is a continuation of the same problem. Here, they're giving you, it's a similar problem. It's not necessarily using the same numbers. Here you've got a sample of 100. We don't need to use that yet. They're telling you that they ran a hypothesis test at 5% level of significance to determine whether the average speed has changed. The p-value is 0.024. They're calling it pp here. It's the same as a p-value. What could they conclude? Well, this p-value is stating that there's only a 2.4% chance of the speed they recorded occurring by chance if the original speed hadn't changed, if the original average speed hadn't changed. This is less than 5%, right? It's more unlikely than 5%. So it's below the 5% of the significance level. So you should reject the null hypothesis. If p had been greater than 0.05, you would accept it, but it's less than 0.05, so you reject it. Now continue on with that same sample of 100. And they tell you that the average speed was lower. They don't tell you how much lower, but they say it's lower. But they ask you to find what that average speed was. So you're looking for an average speed that's lower than the previous average that would produce a p-value of 0.024. Now remember, a p-value of 0.024 means that 0.024 or 2.4% of values are more extreme than the measured value, which means that 1.2% are more extreme in a positive direction and 1.2% are more extreme in the negative direction. So for the positive value, you're looking for an area of PZ greater than or equal to this value of 0.012, and correspondingly the area of 0.012 below the below the corresponding Z value also is 0.012, using the symmetry of the bell curve. So what Z value do you get? Will give you this 0.012 area up here. Well, 0.012 up here, remember the whole area is 1, so this tabulated value would be 1 minus 0.012, which is 0.9888. So we're looking for a Z value at this point, which would give an area under the curve of 0.988. Let's find that in the table. 0.988, it's here, and that's 2.26. Should be filled in here. The other corresponding one for the other side is minus 0.26. So in order to get a p-value of 0.024, they must have had a z-score of either 2.26 or minus 2.26. They're saying the average speed was lower than the previous speed of 87.3. So it must be 2.26 standard deviations lower. In this case, though, you need to work out the standard deviation of the sample. They said the sample has 100 in it. So the standard deviation of the sample using the central limit theorem will be 1.2. So we have the Z, we know the mu, we're looking for the X. Rearranging this formula as usual, you find that the X is mu plus Z prime times the sigma. Plug in the numbers, and we get 84.6 kilometers per hour. And note that that is 2.26 standard deviations below the old average. What we're saying here is that this magazine, they must have measured this speed, 84.6, run it through this calculation, Z, and found a Z score of 2.26 or minus 2.26 in fact, and concluded, well, that means that 0.012 are lower than that. Correspondingly, 0.012 on the other end would be equally extreme. So the total probability of having a more extreme result is 0.024, and that's how they got their p-value. Okay, but we work backward from that to work out what that X must have been, and the answer is 84.6. Okay, I hope that has illustrated some of the techniques. Just quickly to reiterate, you need to read the question and determine what type of question it is. Is it inferential statistics? If so, is it using sample means or sample proportions? And can you use the empirical rules? You see 95% written there. If not, do you have to use the Z-score to get your answer? Again, that's a general set of techniques for figuring out how to do these questions.
I'd like to say thank you, Frank, for a great presentation, very clear with loads of exam questions and examples. There is a lot of information in the log tables. Hopefully we'll see you next week for the 2 exam papers sessions. Okay, so that's all for now.